Okay, in this video we're moving on to Chapter 3, in which we will be solving systems of linear equations. Today we're going to be using tables and graphs to do so. So, as far as vocabulary goes, systems of equations, inconsistent and consistent, dependent and independent systems. These are all terms that we're going to be using today in this video. Our goal is to solve a linear system of equations using a graph or a table. So as a reminder, a system of equations is a set of two or more equations for which a solution satisfies all of the equations in the system. That is, if we can find a coordinate that satisfies one equation, that same coordinate will satisfy the others as well. To solve a system of equations, we generally find a set of values that replace the variables. So variables, independent and dependent, the x and y coordinates. We find a set of values that replace the variables in the equations that make the equation true. So we're going to substitute the letters with numbers so that the equation is true. One side equals the other. To do this, we will often use the graphing method. We can use tables, or in the next video we'll talk about the methods in which we use plain old algebra. So here's our first example. We're going to use a graph to solve this linear system of equations. Now, since we are graphing, let's remind ourselves that in order to graph, we most likely need our equation in slope-intercept form. So I'd like to rearrange both of these equations so that they're in this slope-intercept form. So I'm going to take this first equation from the top and we'll rearrange it this way. So I've got negative 3x plus 2y equals 8. If we add 3x to both sides of the equation, that'll start to isolate our y value. This leaves us with 2y equals positive 3x with a positive 8. Then we can divide both sides by 2. Remember to divide everything on the right side of the equation by 2. And we now have y equals 3/2 x plus 4. So this equation is now set up for graphing. Let's do the same for this other one. So I went ahead and did this one off screen. Hopefully you can see how this answer was obtained. First started by subtracting x from both sides, then divided both sides by 2, and we're left with this equation down below. So now we have to graph them. If I'm going to graph this first equation, I'm going to consider the y-intercept of positive 4, and I'll place a dot on the screen for that. And then from there, I'm going to travel up and to the right 3 units up, 2 units to the right. I know I'm going up and to the right because of the positive slope. So I'll rise up 3 and over 2. And just for good measure and clarity's sake, I'll drop down 3 and left 2 from that original point as well. Now we can see 3 lines, or 3 points that should be connected with a line, and that'll represent this particular equation. I'll connect those dots in just a moment. In this example down here, the second equation, we have a y-intercept of negative 4, but a slope of negative 1/2. So we're going to drop 1 and run 2, or we can rise 1 and run 2 to the left. And now we've got some dots that represent that solution as well. And with this electronic ink, it's a little bit tricky for me to draw a straight line, so I'm going to pause the video and do that now. I'm going to draw a straight line that connects these 3 data points, and then another straight line that connects these 3 data points. Okay, we're back. Now, it's important that when you draw these lines, that you draw them as accurately as possible. Make certain that the lines that you draw go through the 3 data points, and even better still would be to consider what the data points would be if you were to continue your pattern. In fact, if you wanted to draw additional data points as you go, you can do that to help see the line a little bit more clearly. I could have traveled to the left and to the right on both of these graphs to finish drawing this pair of lines. Now what we're looking for as far as the solution goes, remember our goal was to solve this equation. Our solution ends up being the one coordinate that's shared by both graphs. Each graph has a whole bunch of coordinates or ordered pairs that satisfy it, but there's only one, this dot right here, that's shared by both. Now if I look closely, this looks like it occurs at -4 on the x-axis and -2 on the y-axis. So by graphing, we can say that our solution is the coordinate -4, -2. And again, this is telling us that x must be equal to -4 and y must be equal to -2. If I substitute in a -4 for x here and a -2 for y there, then the answer should come out to be 8 after I simplify. And if I substitute in a -4 here and a -2 there, then the answer to that equation should come out to be -8. I would encourage you to pause the video now and perform those checks on your own, and you can resume playback in a moment to follow up with me. And so again, if we substituted in an x value of -4 and a y value of -2 in both equations respectively, the answers that they simplify to on the right-hand side do match what was provided in the problem. So I'm now happy and fully convinced that this is the solution set for this system of equations. Now, rather than drawing a graph of the linear equations, we might be able to solve a linear system of equations by using a table of data. So in this case, we're considering a real-world example where we have a Greenland shark and its growth rate supplied to us, along with the spiny dogfish shark and its growth rate supplied to us. It appears that the Greenland shark at birth is much larger than the spiny dogfish shark. However, the spiny dogfish does grow faster than the Greenland shark. So it would stand to reason that at some point these two will be the same length. Let's see if we can determine when that happens. So one of the first things that I recommend doing is establishing a linear equation for the length of each shark, and we'll let age be our independent variable. We say that that's the independent variable because if we supply the age to this equation, then we should be able to calculate the length of that shark. Age is what drives the length of the shark, so therefore age is our independent value. Now you may also recognize, based on the parts of the table that are already completed, I'm going to go ahead and use function notation for this. So instead of y equals something, I'm going to write g of x. And this is my way of saying that the Greenland shark, its length can be computed based on some input x value. So the Greenland shark's length is going to be equal to, well, we're starting with 37 centimeters at birth plus 0.75 centimeters per year of age. So we can call this 0.75 times x. So that's 0.75 centimeters times the number of years that it's alive, plus the 37 centimeters that it started with. For the spiny dogfish, something similar. I'll use s for the name of this equation. S is dependent upon the letter x. We have a growth rate of 1.5 centimeters per year plus an initial length of 22 centimeters. So now it's just a matter of substituting in numbers. I would need to find g of 15, which would be equal to 0.75 times 15 plus 37. And that's going to give us some length. For g of 16, we'll take 0.75 times 16 plus the 37 and produce some result, and so on. We'll just continue this pattern to fill in this table. On the other side, we'll set it up much the same way. 1.5 times 15 plus 22, 1.5 times 16 plus 22, and so on. You'll see that from time to time I'll use these ... dots to indicate that a pattern is going to continue, or to imply that there's a little bit of math that I'm not showing, but the math itself is relatively trivial. It's something that we've already completed before, or it follows a pattern that we've already established. So that's one way to save a little bit of time and effort and not rewrite the equation every time. So I'm going to switch over to my calculator now and evaluate these, and I'm going to be on the lookout for a pattern. A lot of times in math class we try to look for patterns and utilize those patterns to save ourselves a little bit of energy. So let's see what happens when we start with this Greenland shark. In this first example we have 0.75 times 15 plus 37, and I'm making sure to enter in the calculator exactly what I'd written on paper. If that was the case, then I can trust this result, and I'm happy with that, 48.25 inches. In the next case, 0.75 times 16 plus 37. Now on this calculator, it's kind of nice. If I press the up arrow and highlight what's on the screen here, then when I tap enter, it will copy that down and allow me to make a change and update my computation. So in this case, I got 49 as the next answer. I can't just edit this last line. The calculator won't let me type anything here, but again, by tapping enter, that'll repeat that calculation, and then I can modify it and make some changes. And now we got 49.75. So hopefully you might be seeing a pattern here. In each case, between each line, we're growing by 0.75, or this value is increasing by 0.75. And that's exactly what I would expect to see. If our x values are increasing by 1 unit, then the y value should be increasing by the slope that was described in our equation. So we should see a 0.75 amount of growth for every year. So if I continue that pattern, I'll just add 0.75 to the last answer, and I'll do it again and again and again. This should allow me to fill out the rest of the table. So we've got 50.5 and so on. So that adding of 0.75 between each line continued, and these are results that I've got for the remaining years in this particular table. Okay, so we know how large the Greenland shark will be at 15 years, 16 years, 17 years, and so on. Let's see how large the dogfish shark is, the spiny dogfish. So we'll start by running this equation at the beginning. 1.5 times 15 plus 22. So this should be the size of that spiny dogfish at the age of 15. That's only 44.5 centimeters in length, so 44.5. And then if I run the next calculation, we've got 1.5 times 16 plus 22. We've got 46. We've got 46. And again, we can continue with that last pattern. If I copy the expression from above, change 16 to 17, we can proceed. Or we might notice the pattern that's starting to develop. In this case, we're adding by 1.5 centimeters in length after each row. And after following that pattern, we should see these results. This is the length of the shark after a certain amount of age. Now, you do have to be a little bit careful. The y values will only increase by 1.5 if the x values are increasing by exactly 1. If these x values increased by 2, then we'd have to increase our y values by 2 times that much, or in this case, 3 units. Now, fortunately for us, I think an answer is identified at this point. It's in the 20th row, this 20th year, I should say, that the sharks appear to be the same length. So if we were trying to answer the question, at what age will the Greenland shark and the spiny dogfish shark be the same length, we would say something like this, that at 20 years old, they're the same length. So this question doesn't ask for us to report the answer in coordinate form or with x and y values. They're literally just asking for the age when the sharks are the same length. And I think that's a pretty good answer. Moving on. You may sometimes hear phrases that describe different types of linear systems of equations. A consistent system has at least one solution to it. So if we're talking about a consistent system of linear equations, then there is a solution for it. We can also break down a consistent system a little bit further. We would say that a consistent system is known as an independent consistent system if it has exactly one solution, but dependent if it has infinitely many solutions. So if you're wondering about how that could happen, think about the graphs that occur with linear equations. We have these straight lines. If we have straight lines and they cross one another, they only cross at one point. Those 2 points will only cross one another and they only have one solution. This picture would represent an independent consistent system. But if I had 2 lines and they didn't cross one another, but they in fact laid right on top of one another, if I had 2 lines that occupied the exact same space, well, now they have an infinite number of coordinates that they have in common. It's a bit unusual and kind of strange to think that 2 different lines or 2 different equations might produce the same line, but it does happen from time to time. It's in that case that we would call them a dependent system, dependent consistent system of linear equations, because it has infinitely many solutions. Lastly, we would call a system inconsistent if it has no solution. That means that the lines do not touch or cross one another. And of course, that happens when we're dealing with 2 lines that represent a system are parallel to one another. So, if I start to ask the questions, do parallel lines illustrate consistent or inconsistent systems? Hopefully you recognize that they are inconsistent, and they're inconsistent because no solution is obtained. Or better yet, we can say they're inconsistent because the lines do not touch or cross. Lines must touch or cross to produce a solution. That would be the location, the coordinates of our solution. Now, if I had perpendicular lines, do those illustrate consistent or inconsistent systems? Well, perpendicular lines do cross, and they do cross exactly one time. Perpendicular lines, no matter how they're oriented, will only cross each other one time. So not only are they consistent, but we would also call them independently consistent. So this is an independent consistent system. Now lastly, I wanted to close this video with another real-world example. We have populations that have been reported for the cities of New York and Los Angeles over the last several decades. And we only have data from 1950 up to the year 2000, so there are about 2 recent decades that aren't reported in this table. Maybe we can find that information online to confirm our results that we're about to obtain here. But I'd like to use this table to create a linear regression, which we've seen in prior videos, and then use the linear regression, or the line of best fit, to determine when New York and LA will have the same population in their cities. So if you're in my class in person, we have to jump back to day 11, those notes. If you're just watching this online, it was my video on Chapter 2, Section 5. That's where we talked about scatter plots and finding data that fit. We had this process to establish our line of best fit, in which we can use the calculator to determine that line for us. So if you recall how to do that, now would be a good time to pause the video and try this on your own to recreate this. Otherwise, you can just hang tight for a minute and resume playback in a moment to check what I have produced as the line of best fit. So here's a screenshot from my calculator for the New York data. You can see that I placed the number of years along the x-axis and the population for New York along the y-axis. The calculator started reporting these values in scientific notation, so that's why they look a little bit strange over here. And then along the x-axis, instead of using the entire year, I used 0 for 1950. I used the year 10 for 1960, and so on. And that just allowed me to show this graph closer to the x and y axis and allow the scaling to look a little bit nicer. But what we're after is this result here. This is the equation that represents this straight line. And while it doesn't perfectly strike each of these data points, it's pretty close to all of them, and it seems to split the difference between them. So I've just written that equation over here, and notice I basically just eliminated the decimals that came with that equation. I don't think we need that level of precision here for what we're about to investigate. So for LA, we'll do the same thing. And here's the result from my calculator that I got for the LA example. Notice we switched to the Los Angeles data. Same year setup. We've got another linear equation and the new equation that goes with it. So at first glance, these two graphs don't look radically different. They look kind of similar here when I show them side by side. But it's important to note that the slope of the New York example, the slope that we see here versus the slope of LA, the slope of LA is much steeper. It's a much larger number. So it leads me to believe that the population in LA is growing very fast compared to New York. So I do think that this line on the same scale would be steeper, and I think it will come and intersect the graph for New York. And my suspicion is confirmed. If I graph the New York equation in blue and the Los Angeles equation in red, we can see that they do end up intersecting one another. There is a point where the two graphs cross. That point will indeed represent when the populations will be the same. So that's this number here. Now remember, on my scaling, a number like 86 would mean 86 years after 1950. So 86 years after 1950, I think, is 2036, or approximately 2037 if you wanted to round this. Do you have any guesses as to what this number represents? What does the Y value, even though it looks strange with its scientific notation, what does the Y value represent? Well, this Y valuation would be the population at that time. So after 86 years beyond the year 1950, we would expect the populations to be the same, and that population would be this number if we were to transfer it out of its scientific form. And to transfer it out of scientific form, we just need to move this decimal 7 places to the right. That's what this indication is telling us. So if I move that 7 places to the right, I would end up with an answer that looks like this. And apparently we would say in the year around 2036 or 2037, the populations will be equal, and the population will be around 25 million people. And this is how I would summarize that if I was reporting this on a test or a quiz. I would simply say that in 2036 or 2037, the populations will be equal, and their population will be approximately 25.6 million people. So it does take a little bit of interpretation when you're producing these results, and there might be some rearranging of the numbers, but I think in general you can see the benefit to using this system of linear equations, and especially the graphing method, to find the solution. So I did a little bit of digging just out of curiosity, because at the time of this recording the year is 2024, and so that would mean in another 12 years or so the population should be the same. So if I use the equation for New York and I punch in 73, so I guess technically we're in 2024, but I used 73 for the year 2023. But the model predicts that the population for New York would have been about 23 million people right now. And if I used the number 73 in the Los Angeles calculation, then it predicted that there should be about 22 million people in LA region currently. Now those numbers don't appear to be correct, because according to Google, in the year 2020, so just a little bit before this, we had about 20.1 million. I guess that's not too far off the New York expectation, but we only had 18.6 million in Los Angeles in the year 2020. So even though I used the year 2023 as represented by the number 73, we could actually go back and try this again with the number 70 and see how close those numbers end up being to the results that I found on Google. I'm not going to take the time to do that in this video. I'll leave that up to you as a bit of a challenge. If you have questions, please let me know, and I'll talk to you in class. Thanks for watching.